Now, previously, when proving that diffeomorphism between open subset of the upper half space preserve interior point, we use the following key idea. So if P is an interior point, then we can take an open ball containing P. And the claim is that the image of that open ball is also going to be open. So then, since we contain an open neighborhood of FP, FP must also be an interior point. Now the question is, why is this image open? That will come from this theorem, smooth invariance of domain, which we'll discuss today. The theorem says that if a subset S of a manifold N is diffeomorphic to an open subset of another manifold of the same dimension, then S itself must be open. If we are not careful, we might think that this statement is obvious. We might make the following argument. So, S is the image of U under F, right? Now, F is the diffeomorphism, so F should take open sets to open set. Because U is open, so that means that F of U must be open, so that means that S must be open. Thus, QED. What's wrong with this argument? Well, we were a bit sloppy here. When we say open, we have to say open where? F is a diffeomorphism from U to S. That means that it will take open sets in U to open sets in S. So the most we can say is that F of U, i.e. S, is open in S. It doesn't mean that S is open in N. For example, let's look at the following diffeomorphism, right, from this open interval inside R into this open interval inside R2. This open interval is an open subset of R, but this open interval is not an open subset of R2. Thus, you see the condition that the dimension of M and N are the same is key. Otherwise, if M and N are of different dimension, then as you see in this case, we can have a diffeomorphic image of an open set that is not actually open. Alright, so I hope I've convinced you that this is not so obvious. Now though, before proceeding to the proof, we need to address one point. You're probably very confused about what does it mean for this to be a diffeomorphism if S is not necessarily an open set. Well, for F to be a diffeomorphism, we require that it's a bijection whose inverse is smooth. But what does it mean for this F inverse to be smooth if this S is not open? Technically, we should have addressed that when we define the notion of a smooth chart. Because in that definition, we require this transition function to be smooth, right? But these sets are not necessarily open subsets of Rn, so what does it mean for a function to be smooth on it? So now let's define what it means for a function f on an arbitrary subset S of Rn to be smooth. Well, we would like it to be a local condition, so we'll define what it means for f to be smooth at a point P in this S. But we say that f is smooth at P if there exists an open neighborhood U of P, where this neighborhood is open in Rn. Right? Open neighborhood U of P in Rn, and a smooth function G on U, such that on U intersect with S, G agrees with this f. In other words, f is smooth at P if locally at P it is the restriction of some smooth function at P. Now we say that f itself is smooth if it's smooth at every point of S. So in other words, f is a smooth function if it's locally the restriction of smooth functions in the sense that we are used to. So that's the definition of a smooth function on an arbitrary subset of Rn. Now what if we are interested in function on an arbitrary subset of a manifold, an arbitrary manifold? Let's say h is a function from an arbitrary subset S of a manifold N. What would it mean for h to be smooth at a point P of S? Well, as usual, to be smooth at P is just to be smooth, the same as to be smooth in a coordinate chart at P. Thus, we can combine this h with a chart at P, and now we can define h to be smooth at P if the resulting function, right, h tilde, which is just basically h in coordinate, is smooth. So we bring this back to the case of smooth function on an arbitrary subset of Rn. Alright, so now that we have the notion of smooth function on arbitrary subset, let's come back to our theorem, smooth invariance of domain. So here we have two manifolds, M and N, of the same dimension, and we have a diffeomorphism F from an open subset U of M to some subset S of N. Note that we will define F to be a diffeomorphism if it has an inverse, right, set theoretical inverse, which is smooth. And now we understand what it means for this F inverse to be smooth, because we have defined the notion of smooth functions on arbitrary sets. Now we want to show that S is actually open in N. So let's take a point little s in S, and we want to show that there is a open neighborhood of it that is contained inside N. Now, since F is surjective, we can assume that this point is the image of some point P. We want to find a neighborhood of Fp that is contained inside S. To this end, let's recall what it means for this F inverse to be smooth at Fp. That means locally at Fp it must be restriction of some smooth function g. What do we mean? We mean that there must be some open neighborhood V of Fp inside N and a smooth function g on V such that g restricted to V intersect with S must be equal to this F inverse restricted to V intersect with S. Now we want to show that F must be a local diffeomorphism using the inverse function theorem. So observe that on a small neighborhood here, we see that G composed with F is just going to be the identity, right? Because G agree with F inverse on this neighborhood here, which is V intersect with S. So if we take the preimage of that in U, then we see that G composed with F on that green neighborhood here must be the identity. So by chain rule, this means that this composition of derivative must be identity. In particular, this means that derivative of f at P must be injective. But these two tangent spaces have the same dimension. This is where we use the hypothesis that M and N have the same dimension. So then this derivative actually have to be an isomorphism. Now by inverse function theorem, because this derivative is an isomorphism, we have that F must be a local homeomorphism. Thus, it must send some open neighborhood of P in U to some open neighborhood of Fp in S. In particular, that means that S contains some open neighborhood of Fp, and thus S must be open. Thus, we have shown that a diffeomorphism between an open set of a manifold with an arbitrary subset of another manifold of the same dimension force the second set to be open.